There is a wall above a city in the Peruvian Andes that has quietly humiliated every explanation ever offered for it. It is made of stones the size of delivery trucks, some heavier than a fully loaded semi, and they are fitted together so precisely that you cannot slip a credit card into the seams. No mortar holds them. No cement, no clay, nothing but the cut of the stone itself. For nearly 500 years, colonial buildings raised nearby on flatter, easier ground have cracked and crumbled in earthquakes, while this wall has barely shifted. Now, for the first time, researchers are feeding centuries of survey data, laser scans, and photographs of this site into artificial intelligence systems built to find patterns no human eye could ever catch across so much information at once. And what is starting to come back is forcing a second look at a place people thought they already understood. The site is Sacsayhuaman, perched on a ridge overlooking Cusco, once the capital of the Inca Empire. If you have ever seen a photograph of ancient Peru, there is a good chance you have seen its famous zigzagging terraces, walls that snake back and forth in sharp angles like the teeth of a saw. For generations, the standard explanation has been simple enough to fit on a museum placard: Inca engineers, without iron tools, without the wheel, without written plans, as we would recognize them, quarried enormous limestone and andesite blocks, dragged them up a mountainside using ramps, rope, and sheer manpower, and shaped them by patient trial and error until they locked into place. It's an explanation that isn't wrong, exactly. It's just incomplete, and archaeologists have known that for a long time. The problem has always been the sheer volume of information involved. Sacsayhuaman has been surveyed, measured, and argued over for more than 3 centuries, and that history lies scattered across hand-drawn colonial-era plans, 20th-century photogrammetry, modern lidar point clouds containing millions of coordinates, and field notes in half a dozen languages. No single researcher could ever hold all of that in their head at once. A career might be spent studying one terrace. The next researcher starts over on the next one. That is the real reason artificial intelligence has entered the picture. Not because archaeologists ran out of ideas, but because the raw data had finally outgrown human capacity to process it by hand. Machine learning tools, the kind originally built for image recognition and pattern detection in massive datasets, are increasingly being used across archaeology to spot things buried in noise, subtle alignments, repeated proportions, geometric relationships between structures that are too spread out for anyone standing on the ground to notice. Applied to a site like Sacsayhuaman, this kind of analysis does something genuinely new. It does not look at the wall the way a tourist does, admiring the size of the stones. It looks at the relationships between them, treating every joint, every seam, every angle as a data point in a much larger structure of information. And when you start looking at the site that way, the first thing that jumps out is how deliberate the fitting really is. These are not roughly stacked boulders that happen to sit close together. The stone faces are shaped in 3 dimensions, with rounded, interlocking contours that wrap around their neighbors rather than simply touching flat against them. To cut a single flat seam between 2 enormous blocks using stone and bronze tools is already an extraordinary feat of labor. To cut a seam that curves and locks in multiple directions, on stones weighing dozens of tons, without the ability to test fit and adjust the way you could with something smaller, is a different order of achievement entirely. It suggests not just patience, but planning, an understanding of how the finished shape needed to look before the first strike of the hammerstone. To understand why this matters, it helps to sit with the scale for a moment. The largest stones in the lowest terrace of Sacsayhuaman are estimated by various surveys to weigh well over 100 tons, with some assessments placing the biggest blocks considerably higher. Picture something roughly the size and mass of a loaded delivery truck, quarried from stone that geologists have traced to sources kilometers away across genuinely difficult terrain with ravines and steep grades that would challenge modern heavy equipment. There were no draft animals in the pre-Columbian Andes capable of hauling loads like that, no wheeled carts, no iron. The accepted explanation, ramps, log rollers, woven fiber ropes, and enormous coordinated labor forces working in relays over months or years, is almost certainly part of the truth. Inca administrative records do describe massive labor mobilization for state construction projects, organized through a system of rotating community labor obligations. But moving the stone is only half the puzzle. Setting it precisely into a wall, so that its irregular underside seats flush against the equally irregular tops of the stones already in place, with gaps measured in millimeters, is the harder half, and it's the part that tends to get glossed over in simplified explanations. You cannot easily lift a 100-ton block back out to shave down a high spot and try again. Whoever did this work either got remarkably lucky, over and over, on the largest and most consequential stones in the wall, or they understood the geometry involved well enough to get it close to right before the stone was ever set. This is where the newer, AI-assisted analysis starts to add something the old approach couldn't. By treating the wall as a dataset rather than a monument, researchers can ask questions about pattern and repetition across the entire structure at once, instead of studying one section in isolation. Some of the most interesting recent work in this space has focused not on the stones themselves, but on the site's relationship to the sky. Sacsayhuaman sits within a broader ceremonial landscape around Cusco that Inca planners clearly designed with astronomical observation in mind. This is not speculation. Colonial-era chroniclers, drawing on interviews with Inca informants after the Spanish conquest, described a system of sightlines, called secs, radiating out from the Coricancha temple in Cusco toward shrines and horizon markers used to track solstices and important calendar dates. Sacsayhuaman's elevated position and orientation have long made it a plausible piece of that larger observational network, and researchers have proposed for decades that certain features of the site align with solstice sunrises or sunsets as viewed from specific vantage points. What computational analysis adds is the ability to test many possible alignments across an entire site simultaneously and check which ones are statistically meaningful rather than coincidental. Comparing a handful of true celestial correlations against the enormous number of angles you'd expect to find lining up with something by chance alone in a structure this large. That kind of rigorous, systematic checking is exactly the sort of task that benefits from computational tools, and exactly the sort of task no lone researcher with a notebook could realistically perform across an entire terraced hillside. It's worth being honest about where the evidence is strong and where it remains genuinely debated. The idea that Inca builders tracked solstices with real sophistication is well supported, both by colonial documentation and by architectural sites elsewhere in the empire built explicitly as solar observatories, like the Torian at Machu Picchu. Extending specific solstice or lunar standstill claims to particular joints or stones at Sacsayhuaman itself is a more contested, ongoing area of research, and serious archaeologists disagree about how much of the wall's layout was shaped by astronomical intent versus defensive and administrative practicality. Any honest account of this site has to hold both possibilities at once rather than presenting one interpretation as settled fact. What AI-driven analysis is genuinely useful for is narrowing that uncertainty, by systematically ruling out alignments that don't hold up and flagging the ones that survive rigorous statistical testing for archaeologists to investigate further on the ground. There's a similar story with the acoustic properties of the site, an area of research that is much newer and far less established, but that has started to draw serious interest. Large stone terraces and enclosed courtyards can behave in unexpected ways acoustically, reflecting and focusing sound in ways that flat open ground does not. Some researchers studying ceremonial sites across the Andes and elsewhere in the world have begun modeling how sound would have moved through spaces like this using acoustic simulation software, the same kind of modeling used by engineers designing concert halls. Preliminary work at a handful of ancient sites has found that certain chambers and courtyards do concentrate sound in specific frequency ranges in ways that seem intentional rather than accidental. Though this remains an early and specialized field, and claims about Sacsayhuaman specifically should be treated as an active hypothesis rather than a confirmed finding. If ongoing acoustic modeling of the site does eventually show that its geometry shapes sound in a deliberate way, tied to the same spacing that may carry astronomical meaning, that would suggest something remarkable. That Inca builders were solving two very different engineering problems, sight and sound, using the same physical layout, which would mean the wall's dimensions weren't arbitrary, but the product of layered, deliberate design constraints working together. What's genuinely striking, and well documented regardless of how the more speculative astronomical and acoustic questions eventually resolve, is what the stonework itself tells us about how this knowledge moved through time. Careful survey work across the site has long noted differences in precision between construction phases, generally attributed to the site being built and expanded across multiple periods of Inca rule, possibly under different rulers with different priorities and different access to skilled labor. Some sections show the extraordinarily tight, almost seamless fitting the site is famous for. Other sections, believed to be later additions or repairs, show looser, less precise work. Archaeologists have proposed a range of explanations for this: shifts in available labor, changes in the urgency or purpose of construction, or simply the reality that the most skilled masons may have concentrated their effort on the most important, most visible sections of wall rather than every single stone. Framing this as evidence of forgotten knowledge makes for a dramatic story, but the more grounded explanation, that construction quality varied across a long building history involving different teams and different priorities, is both more likely, and honestly, still remarkable enough on its own. It tells us this was never a single, uniform building project. It was an evolving one, shaped by generations of decisions we are only now able to reconstruct in detail. And that reconstruction is really the heart of why AI-assisted analysis matters here, beyond the headline-grabbing possibilities. Sacsayhuaman was partially dismantled by the Spanish after the conquest, its stones repurposed to build colonial Cusco, which means a significant portion of what once stood on this ridge is simply gone, surviving only in fragments, foundations, and the handful of massive lower terrace stones too large to easily move. Piecing together what the complete site once looked like, how its different sections related to each other, and what functions different areas served: defensive fortress, ceremonial temple complex, administrative center, or some combination of all three, is exactly the kind of large-scale pattern-matching problem where computational analysis genuinely outperforms manual study. It can hold the entire site, including the parts that survive only as scattered foundation stones logged in decades-old survey reports, in a single model at once, and start testing relationships between fragments that no individual researcher walking the site would ever think to compare. None of this means the mystery is being solved by a machine handing down verdicts from on high. What these tools actually do is much more modest and, in its own way, more interesting. They let researchers ask better questions faster, and check old assumptions against far more data than was previously practical to analyze by hand. The people who built Sacsayhuaman left no written records in the way we typically think of them, no blueprints, no engineer's notebook explaining the reasoning behind a given cut. What they left is the stone itself, and for centuries our ability to read it has been limited by how much of it any one person could study in a lifetime. That limitation is finally starting to lift, not because artificial intelligence has some mystical insight into the ancient world, but because it can hold and cross-reference more information than a human mind reasonably can, and flag patterns worth a trained archaeologist's close attention. So where does that leave us? With a site that was already extraordinary by any honest measure, made more so by every new layer of careful, rigorous analysis, rather than by exaggerated claims that don't hold up to scrutiny. The wall that stands above Cusco today was built by people solving real engineering problems, moving impossible weights up real mountainsides, and very likely encoding real astronomical knowledge into the way they laid out their most important structures, using methods that remain, in places, genuinely difficult to fully reconstruct. That is not a story that needs embellishment to be compelling. It's a story about human ingenuity operating at the edge of what seems possible with the tools available at the time, and about how new tools, 500 years later, are finally letting us catch up to understanding just how much thought went into every single stone. If a site like this can hold this much unresolved detail after 3 centuries of dedicated study, it raises an obvious question worth sitting with. How many other ancient sites around the world are we still looking at with the wrong scale of attention, waiting for the right tools to finally read them properly?